some positive, I don't know if it's or not.
No, if the questions are like, what happens in paragraph 16? Am I gonna read 1 to 16 and get to paragraph 16?
Go to paragraph, you guys.
And then like read around the front page?
Yes.
I thought it was so cool.
The what?
Okay, everybody.
Nobody's like old now.
Yeah. Well, I think he's really. Yeah, he's 14.
I think his mom owns his Instagram.
No, they said.
So I was going through my stories and someone posted like something like that. I don't know if I haven't seen that
Wait,
TikTok.
well, look at all that story. I think it's so many. 2006. It sounds like that he does not.
No.
I read the software, like the software. Actually read them. But that's somehow I read that.
All right, everybody.
It was just about like a regular. Like they didn't like stare.
Can I get everybody's attention? We don't have a ton of time.
We would have to, I know they don't.
Can you tell me? Because I actually don't remember.
8:27.
Okay. All right, everybody. So we're going to start off with simplifying radicals. You have seen this before, so that should be easy peasy. And then we're going to make things a little more interesting. So you remember, of course, if I ask you, hey, what's the square root of 81? You know that that answer, of course, is just 9. Sure. Now there is, you could say, well, isn't it positive and negative 9? So let's have that conversation right now real quick. So if I just write square root of 81 like this, it is implied that I only want what is called the principal root, which is just the positive root. If I wrote this, that is obviously going to be a negative 9. And then if I did want both roots, if I want, because it is true, like the square root of 81 is both positive and negative 9. So if I wanted both, you're going to see it written out in front as both, and then that you would give an answer of both positive and negative 9. Okay, so when you see it without any symbol in front of it, you can just give the principal root, it's called, which is just the positive. Okay, so we remember square roots, right? Now, it's easy when the number you're taking the square root of is what we call a perfect square, right? 1, 4, 16, 25, easy peasy. What happens when it's not a perfect square? Well, you could grab your calculator and figure out a decimal, but you can also simplify the radical. So let's just start off with something like the square root of 50. 50 is not a perfect square. But if I think about the numbers that are perfect squares, 1, 4, 16, 25, 36, 20 of those numbers divide into 50 evenly.
25.
25. So what I can do is it's just like reducing a fraction. I'm going to reduce this radical by finding a perfect square that does divide into this one, preferably the largest perfect square that divides it. So in that case, it's going to be 25. So just like you made factor trees in like elementary school, I'm going to make a factor tree and I can split that up into the square root of 25 times the square root of 2. This is 25 times 2, just 50. Right? Easy peasy. And now I know what the square root of 25 is. It's just, well, yes, it's 5. So this whole thing just becomes 5 root 2. So that's old news, right? You've seen this before, you remember? So let me give you another one to try. How about the square root of, I don't know, about 300. Sometimes it's helpful to, I'll just make a list of the perfect squares along the side. Sometimes it's easy just to have them like in your face. You don't have to, but if you want to have them in front of you, you can. So, if I'm doing like a test or a quiz or something, I might put them there just so I like have them right in front of my face. But all I'm doing is, that's just my list, 1 squared, 2 squared, 3 squared, 4 squared. So if I'm looking at the number 300, I want the largest number in my list that divides evenly into 300. Jimmy, it's 100, right? So I would just split this one up into the square root of 100 times the square root of 3. And that's easy peasy because the square root of 100 is just 10. So this whole thing just simplifies to be 10 root 3. Isn't that easy? I always put the perfect square first because just like you start a sentence with a capital letter, you put the number in front of the root. So if you have a square root as part of your number, it always gets tacked onto the end. All right, let me give you one more. Oh, by the way, I wonder, did anybody do this one? You're like, oh, 25 goes into 300. That's true, but it's not the largest perfect square that goes in. So let me just show you really quick. If you don't pick the number that has the largest square root that goes in, so don't write this down, or you can if you want. If you had said, just pick a number that goes in, oh, 25. Well, 25 does go in, what is it, 12 times? So you get 5 root 12. The problem is that's not done because doesn't 12 have a perfect square that goes into it also? Then you have to do it again. It's just like if you were reducing the fraction, I don't know, 10 over 50. Instead of reducing by 10 and you just reduce by 2, now you're at 5 over 25. You got to do it again. So try and find the biggest perfect square that goes in, and then you don't have to worry about it. Because now here, I'd have to split this one up again. 12 splits into 4 times 3. You still have this 5. So now look at all this extra work you're going to do. 5 times square root of 2, 4 is 2. Look at that. You basically did double the work. So I don't advise that. Just take the 3 seconds to find the biggest perfect square that goes in. But if you don't, all's not lost. You just got to do it again. Okay? So just make sure your answer is fully simplified. And you know that it's fully simplified because that number under the root does not have any perfect squares that divide into it other than 1. So 1 goes into everything. All right. Old news, right? Do you remember how to do operations with radicals, I wonder? Like if I were to ask you the following. Hey, how do you do 5 square root of 3 plus, I don't know, 7 square root of 3? You remember how to do that?
Yeah.
What would that be? What's your answer? Yeah, it's just like the radical, as long as they are like radicals, just like terms, I do the same thing. I'm just going to combine the numbers, the coefficients here. I'm just going to combine these together. So 5 of these things and 7 of these things would make 12 of these things altogether. Easy peasy. Let's try multiplication one. What if I asked you to do square root of 2 times 4 minus square root of 3? Go ahead and try that. What do you think that's going to look like in the end? Okay, who thinks they've got the answer? Go ahead, Sam.
4.
Perfect. So things that are, when you multiply the root 2 times the 4, I can't really do anything besides multiply them together like that. It just becomes 4 root 2 because they're not both under the radical. But when I do the root 2 times the root 3, they are both under the radical. So I can multiply them together. Thank you. Oops. Did you get stuck in that bus situation? Oh. They haven't said that that's cleared yet. So anyway, so yes, if they're both in the radical, you can multiply them together. If they're not, well, you just multiply them. It's just like variables, right? What else before we get to the good stuff? What happens if you have a radical in the denominator? Do you remember? That's a big no-no. So let me put a little star. You cannot leave a radical in the denominator. By the way, you know what I mean when I'm saying radical, right? It's just the square root thingy, just another name for it. You cannot leave a radical in the denominator. Why? That's a great question. I have no answer for you. I don't know. It's called rationalizing the denominator. So if you hear that term, rationalizing the denominator. I'm going to be perfectly honest with you. I always rationalize the denominator because that's what I was taught you had to do. And then when I was in graduate school, I took a class that was like, it was 4 teachers. So it was all like, we were all math teachers. And then the professor was just like a normal college professor. And so we're all doing this and we're all rationalizing the denominator. And he's like, what are you guys doing? We're like, what do you mean? What are we doing? Rationalizing the denominator. He's like, why? We're like, I don't know, because you're supposed to. He's like, you don't have to do that. Just stop doing it. So it wasn't until I got to grad school, they were like, it doesn't matter. It's the same number. Why is it a thing? I have no idea. Someone at some point said it was. Yes.
And then I think it was like, so it'd be a complex fraction of the
I guess, but what's so bad about it? Why can't you have a decimal and a fraction? It's the same number. So am I. I'm complex. I don't know. I'm anti-rationalizing the denominator. However, it's not up to me. So we do have to rationalize the denominators because I don't rule the world, right? Not that I want to, too much responsibility, but I'm going to show you how to do it, okay? But I want you to understand it's the same number. If you put it in the calculator with the square root in the denominator or without, you will get the same number back out. Mathematically, it does not matter. But it's just like, why do we start sentences with capital letters? I don't know, because it's the same word, right? But that's the convention that we have come to accept. So, huh?
No, I'm just kidding.
I didn't hear what you said.
It's okay. I said what's a convention,
Oh,
but I was just kidding.
okay. Well, for those that don't know, a convention is just like the way that we do things. Yeah. So let's talk about it. If I have a square root in a denominator, say I had something like 7 over the square root of 3. If I'm not allowed to have that down there because someone at some point decided that I can't, all right, fine. How do you think you'll get rid of it? Let me go back. Oh, multiply by what? Yes, you basically need to undo the operation, right? So undoing addition, we subtract. To undo multiplication, we divide. To undo square rooting, I square something. But you can't just go around squaring numbers, right? If I could, I would take my bank account and I would just square it, wouldn't you? Oh my gosh, it'd be so easy. So I can't do that, but I can multiply by 1. Right? And that doesn't change anything. I can take my bank account and I can multiply by 1 and I still have the same amount of money that I had a second ago, right? Right. That's basically what I'm going to do. But I'm going to disguise it as squaring the bottom number. Check this out. If I multiply by the square root of 3 over the square root of 3, isn't that just 1? Isn't root 3 over root 3 just 1? Right? Like 5 over 5 is 1. 15 over 15 is 1. Right? But look what happens. The numerator, 7 times root 3 is just 7 root 3. But what is the square root of 3 times the square root of 3? It's just 3. Look at that. So here's my claim. Whoop. I can show it to you on a calculator too if you want. If you take this number, my original, type it into a calculator, and this number, type it into a calculator, they will be the exact same number. They are the same. The only difference is that you have gotten rid of the square root downstairs. Does that make sense? Are you with me? You remember this from algebra 1? Little bits? Okay. Does it get more complicated? A little bit, because what happens if we try and do this? Check this out. What if I did like 4 over, I don't know, 3 minus the square root of 2? So I know what you might be thinking at first. You might be thinking, oh, hey, can I just multiply by square root of 2 over square root of 2? That's what you just did before. Can I do that again? What'd you say? Yeah, you gotta, if you do that, you're just gonna move the square root from right here to right here. It's still gonna be in the denominator. You're just gonna get 3 root 2 minus 2. Well, that's inconvenient. Hazzy, how do we fix it? Yes. You multiply by what's called the conjugate. It's the same 2 numbers. I'm just gonna change the sign in the middle. So check this out. On top, I'll multiply by 3 plus root 2. And I have to do the same thing top and bottom, because remember, I'm really multiplying by 1. So as long as I have the same thing on top and bottom, I really am multiplying by 1, and I'm not breaking the laws of math. I'm allowed to do this. But look at what happens when you multiply straight across now. So I'm doing a monomial times a binomial. I have to distribute. So 4 times 3 is 12. 4 times root 2, I get that 4 root 2. Right? Let me switch to my orange. Bloop. And bloop. Look what happens in the denominator. You ready for this? Watch this magic. I have 2 binomials. I gotta FOIL this. Just like last night's dinner. 3 times 3 is 9. Outsides plus 3 root 2. Insides minus 3 root 2. And then last, what's a negative root 2 times a positive root 2? Negative 2, right? When you, the radicals are going to cancel each other out, and a positive times a negative is negative. Look what happened. Do you see? Look, a plus 3 root 2 and a minus 3 root 2 just cancel each other. And now you just have 9 minus 2, which is just 7. Wow. How fancy. So you just went from having a square root in the denominator to not. And all you had to do was multiply by the conjugate. Do you remember you hearing that word, conjugate? I'll put it on here. Conjugate. Same binomial. Just change middle sign. Only the middle, the sign in the middle. You don't change the sign for both numbers. Just change sign in the middle. Oh, sorry. Little off. Okay. Yes, Jimmy. What do you mean? The homework? Or the video that I'm making, or the notes? Notes for sure. Video for sure. Homework for sure. Just like every other day. I'm after school every Tuesday. I'm after school every Tuesday. Yeah. Go so fast. All right. I gotta flip the page because now we're gonna get to the real good stuff. Are you ready? You better go fast. Oh, I don't know where it is.
It's also both passes.
There used to be 2.
They're probably called trash.
Maybe. All right. Okay, you ready? You ready? Oh my gosh, this is so exciting. What if I asked you to take the square root of, let's go with -16? You already know the answer? Well, hold on to it for 1 second. How do you know this?
I know that was a V and Scott's.
Wow.
Yeah.
Well, I guess it's all old news then. But maybe if some of you may not have seen it. You might be thinking at first, well, isn't it just -4? No, because isn't -4 times -4 +16? It is. So what in the world am I supposed to do with this thing? Tell me what the answer is.
4 times.
Yes. So we have this cool thing called the square root of -1. And we have called that, we've given it a variable. Well, it's not really a variable. It's not a variable. We've assigned a letter to the number I. Lowercase I, just like that. So I is just the square root of -1. So instead of just writing the square root of -1 over and over and over again, it makes things way more complicated. We just said, hey, let's use the letter I instead. And I assume it represents imaginary numbers. That's the group of numbers that this falls into. Imaginary. So remember that you have the real number system, which is broken up into the rationals and irrationals. And basically all of the numbers that you talk about are in that real number system until you hit these. These are imaginary numbers, square roots of negatives. Oh my gosh. And I can simplify them kind of similarly. So what I can do is I can say, oh, hey, well, let's just split that up into the square root of 16 and the square root of -1. I know what the square root of 16 is. It's just 4. And now I've just learned that this thing I'm going to replace with just the letter I. So that just becomes 4i. Oh, that wasn't so bad. So if I wanted to do something like the square root of -49, what would that be? 7i. For the same reason, I'm splitting it up into 49 and -1, take the square root of each. So I can even do it when it's not a perfect square. If I wanted to do like the square root of, oh, I don't know, something like -32. So what's the biggest perfect square that goes into 32? 16, right? I know 4 does go in, but I have a bigger one. I have 16. So I might split this one up, and this is how I do it. I would do the perfect square, 16, times 2. Oh, no, I wouldn't. I guess it really doesn't matter. It's all multiplication. So see, I really made 3 branches. And now if I put it all together, here's the way that we write this. You have your whole number first, so that'd be a 4. And then if there's gonna, ooh. Yeah, I think we put the I, and then we always put the radical at the very end. Even though that's a radical 2, so, but it just would be weird if you put the I on this side, it'd be confusing, like, is the I under that or not? So if you have an I, put it before a radical. But if there's just an I, the I always goes at the end. Does this make sense? Everybody okay so far? So you try this one. How about the square root of -98? See if you can simplify that one. So what's the largest perfect square? Jimmy, go ahead.
7.
Yes. I have a sneeze coming. But now that I said it, it'll go away for like 2 minutes and then it'll come out of nowhere. All right. Yes, this splits up. I'm going to do it 3 times. 49 times 2 times the square root of -1. So when I sort of unpack all of that, I get a 7, and then I'm going to put the I next and then the root 2 on the end. So 7I root 2. Now, what's so nice about I is that when you're doing operations with it, it acts just like any other variable. So if I were to ask you, hey, what's 4I plus 6I? That's the same thing that you would do if it was 4x plus 6x. Your answer would just be 10I. The only time it gets a little weird is when you're multiplying and you get an I squared. Kind of. If you take the square root of -1 times the square root of -1, what do you think comes out? You're kind of close. It's -1. They basically just undo the radical signs. So big star, because this is super important. I squared is just -1. So anytime you see an I squared, you can replace it with a -1. So let's do an example like, let's do, what do I want? Let's just do let's do 2I times 3 minus I. Let's do that. So at first, I'm going to treat I just like it was any other variable, right? So if those were just X's, I'm just going to distribute like I always do. So let's try that. If I do 2I times 3 and then times the -I. So what would 2I times 3 get me? 6I. And then 2I times -I would get me. You're right, but don't do that part yet. If I'm just treating it like a variable, don't I get -2I squared? Right? Just like if those were X's, so that would be a -2I squared. So now that I've done the distribution part, I go back and I look and I'm like, oh, I have an I squared. That's really a -1. So what that now turns into, I have 6I minus 2, and now I have times a -1. So that's my only change. So I can simplify that. That becomes 6I plus 2. And if you want to be real fancy, if your answer does have an I in it at all, that should be going at the end. So it would be best if you rewrote it as 2 plus 6I. And then the only thing I have to show you, I just want to show you what happens. The same thing is true when you have I in the denominator, because I is a square root, and you're not allowed to leave square roots in the denominator. So I have to fix them. So if I were trying to do that, say I had something simple like, I don't know, 4 over 3I. So if I wanted to fix that, what can I multiply by to undo this? Yes, I over I. Now, a lot of times kids will multiply by 3I over 3I. You're not wrong, but you're making your life more complicated. Because the 3 is not the problem, it's the I that's the problem. So to handle that I can just literally multiply by I over I. And watch what happens. Up top, I get 4I. On the bottom, isn't that now just 3I squared? 3I squared, which remember, oh, I have an I squared. It just turns to a -1. Ah! So this is now just 4I over -3. Or -4/3 I. Isn't that neat? And then, yes, what happens when you have that binomial situation with an I? Same thing. I'm going to multiply by the conjugate. So check this out. What if I had, let's do 2 over, I don't know, 5 minus I. You see this? You're like, oh, that's a problem. I'm going to fix it. And I'm going to multiply by
5 plus I.
yes, 5 plus I on top and on bottom. When you do that on top, remember you're doing a monomial times a binomial, so you gotta distribute, that's 10 plus 2i. No problem. Downstairs, here's my claim. This is a bold claim here, so I better be able to back it up. I claim that when I do this, I won't have eyes at all anymore. What? The eyes are just gonna disappear? Yes. Let's try it. We got a FOIL first, 25. Outside, a positive 5i. Inside, a negative 5i. And then last, what's negative I times positive I? Negative I squared, right? Because you're treating it just like a variable right now. If those were x's, I would just negative x times positive x would be a negative x squared. All right, cool, cool. Look at this magic. A positive 5i and a negative 5i cancel each other out. Eusebia, I thought you said that the eyes would disappear. You still have one. You're such a liar. Am I? Am I? It's really, it's I squared. So that I squared turns into a negative 1. But it's so now you have negative negative 1. Isn't negative negative turn into a plus 1 on the end? You see that? So this turns into 25 minus negative 1. And that's how I really end up with 25 plus 1, or 26. So my denominator is actually just 26. Oh, I'm actually so glad that this answer came out like this. Is this a final answer? 10 plus 2i over 26? Is that an okay answer? Hannah, why not? You can reduce, yes. Look at, and here's how you know. Look at all these numbers. 10, 2, and 26. They all have a common factor. All 3 of them have to have the common factor. It can't just be 2 of them. So if that had been like if this number right here was like, I don't know, a 7, you can't just cancel the 10 and the 26. That's a huge no-no. It has to be all of them or none of them. Okay, but I can reduce them all by 2, so I will. So that just becomes 5 plus I over 13. And that's my final answer. Holy moly. That's a lot of guacamole. Huh? Look at that. How nice. And look, no i's in the denominator. That was our whole goal. But how frustrating to know that this is literally the same number that I started with and I did all this work for no reason. But anyway, that's neither here nor there. Okay, that's it. You guys have questions? No, you sure? Yeah. You gotta get rid of it. So if you end up with one here, after you did this, like if this answer still has an I in it, you messed up somewhere.
Oh.
Yeah.
Oh, yeah.
Yeah. So if you are multiplying by the conjugate, that should take care of it.
Yeah.
But if it still is there, you know what? That's actually a great question because sometimes what kids will try and do, you guys don't have to write this down, but I'm just going to show you real quick. So if I start with that same original, sometimes kids will try and get rid of the I by just multiplying by I over I, and watch, it's not going to get rid of it, right? You'll have 2i on top, and then on the denominator, you're going to have 5i minus I squared. So that one's going to change. So now you have 2i over 5i plus 1. You still have an I down there. So you're like, oh, great. So I did all that work for nothing because it didn't get me anywhere.
You lost me.
He asked why, what happens if you still have an I in the denominator? So my answer is you messed up. Because you should have multiplied by the conjugate, right? Not just, so that, I'm just showing a common mistake is that you just multiply by I.
Okay.
So let's
Keep an
put
eye
a,
out, Miss Sabia.
let's put a big X.
Oh my
Keep an eye out
God.
for you.
I saw.
Oh, God, it was 37.
27.
Oh my gosh. Well, I guess there's no homework because I didn't get to hand it out to you.
Oh.
Such a bummer.
They're heartbroken.
Yeah.
Hey, are you, sorry, this is sitting here.
Oh.
Are you
the environment stuff. I have a senior in the lacrosse team that needs to do the impact test, so I just have to go there do mine.
Will she find that out for me?
She will not mind the answer.
Okay.
Do you have the answers to the?
I really want to sign it.
I really want to punch you in the nose with my
Aren't
gun.
they attached to the back?
No, that
It's
was
all
the
hard
other
now.
one. This one's all
Yeah,
hard
I think
now.
it's, hold on.
This one will hurt.
Oh, God.
Don't forget.
Yeah, it's on the back.
Oh, I didn't know.
Yes.
Okay.
You're welcome.
That's good.